Hi, my name is Alejandro Medrano, and this is the final delivery of my key activity of physics. In January, during the Topicals week, I had the opportunity to have an aerodynamics class. Guided by the question, how does the shape of a body affect on its aerodynamics when it's subjected to wind against it? We were able to perform an experiment and therefore understand the topic better. During the first 2 days, we did a brief research about the topic. And then during this class, we worked on the creation of 3 car-shaped models with different curves on their bodies, but all of them of the same material, with the goal of making them similar, but the hypothesis that because of their shape, they will have different aerodynamics. Aerodynamics is the study of properties of moving air and the interaction between the air and bodies moving through it. We use the drag coefficient to measure aerodynamics and is calculated by the following formula. Drag coefficient is equal to the drag force over half the density of the air in contact with the object times the area times the frontal area projected times the velocity of the running wind square. In this project, since we're subjecting bodies to a subsonic wind tunnel looking for something, the drag coefficient, both are independent variables, wind and the bodies. In this case, the dependent variable will be the aerodynamics of the bodies, which we will consider as the drag coefficient of each body, calculated from the drag force measured in the experiment. The materials needed for this experiment are a subsonic wind tunnel, just like this one, and all its accessories, as well as the 3D printed bodies, and a notebook or something to take notes on. We performed this experiment at Tecnológico de Monterrey, Campus Monterrey, and the first thing we did was gather all our things and went to the lab where the subsonic wind tunnel was. Next, we took body A that was going to be subjected to the wind tunnel and attach it to a very thin bar. This bar was the only thing from the outside going into the inside of the wind tunnel besides the body, and it's also one of the accessories of the wind tunnel. Next, we turned on the tunnel, and with help of some speedometers at the outside of the tunnel and some instruments to measure pressure, we subjected the body to 3 velocities, one at a time. The 3 velocities were 10 meters per second, 15 meters per second, and 20 meters per second. For each velocity, we measured
wind
the
tunnel
drag
for
force
study in
based on a weight scale that
aerodynamics.
was
Tech
attached to a
Equipment's
thin
range
bar
of models
where we
allows
attach
for a
our body.
wide variety of subsonic
The scale
aerodynamic
was working was
experiments,
with newtons.
including investigations into boundary
The
layer
thin bar
development,
will
aerofoil
move
performance,
while
pressure
the body attached
distribution,
to it was
and
subjected
measurements
to
of
wind,
lift, drag,
making
and
the scale
pitching
move
moments.
too.
The
When
AFA-10
we
smoke
balance the
generator
scale,
allows for flow
The
visualization
body
around the models.
attached to it was
The
now
sides
facing
are
the wind
removable on
and
the
not being
working
dragged.
section to allow
And
for
that's when we
easy
measured
access to the models.
the
The
drag force.
FA100 comes
In
with
order to
either
prevent
basic
air
balance or a
forces trapped in the
3-component
tunnel,
balance
we
to
made
allow for
sure there were
measurements
no
into
holes
lift, drag,
where the air
and
could
pitching moment.
escape or get
A
into the
separate
tunnel,
control and
releasing it first
instrumentation unit
without any
controls the
object.
speed of the axial fan.
We took notes of the drag forces of the 3 velocities in the body, and then repeated the same process as we did with object A, with object B and C. Once we had all the 3 forces, we calculated the drag coefficient in order to determine which of the bodies is the most aerodynamic. We calculated this drag coefficient by using the same formula we previously explained. These were the results we got. In the first column, you can find the body the measurement is referring to. In the second column, you can find the velocity that we subjected the body to. In the third column, you can find the drag force, and in the fourth column, you can find the drag coefficient that we got from the drag force and the velocity. We can see that in all cases, body C was the most aerodynamic, since it had the lowest drag coefficients, and the lower the drag coefficient, the more aerodynamic the object is. One challenge we had was that we needed to measure the drag forces manually, while nowadays, there are many programs for computers that measure this drag force by using an instrument attached to a wind tunnel. We can conclude that the more softened the edges of the shape of a body, the more aerodynamic it will be.